Hey guys, Buildzoid here, and today we're going to be taking a look at the PCB of the ASUS RTX 4090 Matrix. The PCB pictures were provided by ASUS, so big thank you to them for sending those over. And before we get into this, a quick disclaimer. This is not a review, and I'm not an engineer. And with that out of the way, let's get into it. So, the 4090 Matrix is basically a Strix. There is one difference that's actually kind of cool and noteworthy, and the whole reason why I actually decided to make this video, or why I'm like pushing myself to make this video, because I've been sitting on these photos for ages. It's really hard for me, like, I don't know how to structure a video where it's like, this is a Strix for like 90% of the PCB, and then there's like one difference, and it's like, do I just go over the Strix PCB breakdown? Anyway, so things that haven't changed. The voltage controller is still the same monolithic power systems, or like the main voltage controller on this card is still the same monolithic power systems 2891, still running in a 12 plus 4-phase configuration, so you have a 12-phase V-core VRM with 2 power stages per phase, so 24 power stages in total, and then the plus 4 for the memory, which is exactly like, that's just standard high-end 4090 things, is 4-phase memory power. The capacitors haven't changed, so the same input filtering capacitors, right? I mean, I'm not even going to deal with, like, they're the same. Like, you could literally overlay these two PCBs together and it would just look the same. Anyway, output filtering is also the same and really good. Like, it makes sense to me that ASUS didn't really bother to change the power delivery in any way, shape, or form going from the Strix to the Matrix, because as far as I'm concerned, the Strix PCB is already one of the best RTX 4090 PCBs out there. It has a ton of output filtering capacitance that uses the best voltage controller that you can get for a 4090. The ton of output capacitance is in actual, like, as far as I can tell, Panasonic SP cap, so it's very low ESR, very low ESL. There's not really much to improve as far as I'm concerned when it, like, in terms of the power delivery on a 4090 Strix. So yeah, I can't say I'm surprised that the 4090 Matrix has the same power delivery for, well, mostly the same. There is one difference, but I'm not even sure that's an intentional design choice, and we'll get to that soon enough. But anyway, while we're on the back of the card, I also wanted to point out that ASUS is labeling the various, like, voltages on the card, which is pretty cool. If you're potentially, if you're trying to repair one of these, this could make your job a bit easier. Instead of like trying to instead of like having to manually figure out which power rail is supposed to be what. So yeah, that's pretty cool. You even have a label for ground and like 5 volts. So yeah, I think that's like a neat little extra that ASUS puts on their cards, and they do this on all of their cards these days. So yeah, neat little extra that you get. What else do we have? Oh, there is dual BIOS on the card. There's a switch for that up there, and there's some LEDs to indicate which BIOS is active. Yep, you can see them over here and here. Anyway, so yeah, same controller, same phase configuration, same capacitor configuration. I think apparently the inductors are supposed to be low coil whine or something, but I don't really have a way of verifying that. And apparently, and I'm pretty sure they're rolling that adjustment to all of the PCBs. So yeah, this is basically a Strix in terms of the stuff that I usually cover in my PCB breakdowns, because the extras on this card aren't usually found on GPUs, or like the one extra on this GPU isn't usually a thing you see at all. But anyway, so yeah, power delivery is very similar. However, there is one difference, but I'm not sure if this is an actual design choice, and that is the power stages. When I did the PCB breakdown for the Strix, the PCB for the 4090 Strix that I was looking at used Fairchild Semiconductor, now On Semiconductor, because Fairchild got bought by On Semi. But yeah, that used On Semiconductor FDMF 3170s, whereas the 4090 Matrix PCB that we have here is using monolithic power systems MP 86957s. Now, these are, like, the thing is, I'm not sure if this is an intentional design choice from ASUS, or if or if On Semiconductor simply ran out of power stages, because that is a very real concern for GPU manufacturing these days. That like your first choice of power stage supplier will just run out of the power. Like they'll just run out of power stages. Some data center, like because the power stages that get used on 4090s also get used on like data center hardware. So um, it's not impossible that you just run out of power stages. Um, and so it's actually quite common to see 4090s where like the same model of card comes in like 3 different flavors of power stages, each from a different supplier, because of just making sure that you can actually manufacture cards. So yeah, so I'm not sure if the switch from the FDMF3170 to the MP86957 here is like an intentional design choice, or if the 3170s just ran out. Because yeah, I don't know. Either of those is a possibility. Now, functionally, in terms of what this means for performance, the MP86957 is nominally a 70 amp smart power stage. The FDMF3170 is also nominally a 70 amp smart power stage. And instead of doing all of the calculations, I figured I'd just show you the typical performance characteristics for these and like overlay them on top of each other. Because these power stages do actually have public data sheets. I'll put links to those data sheets down in the description. So anyway, here we have the typical performance curve for a FDMF 3170. You will notice that it does not go, oh boy, this is going to be awful. Yeah, so you'll notice that it doesn't go over 60 amps, even though this is nominally a 70 amp smart power stage, and there's a very simple reason for that. At 60 amps, this thing outputs 12 watts of heat. So at 70 amps, it's going to be completely uncoolable. Or at least, okay, not completely uncoolable, but impractical to cool. If you're actually designing a voltage regulator, you're probably going to not design it to require like water cooling to function, right? So the fact that the power stage is like technically under very specific operating circumstances, you can get them to output 70 amps is not really practical. But that's what the like nominal current ratings generally indicate, at least with the really high current parts. Because there's like low power stages, like 35 amp parts, where you could actually realistically hit the 35 amps, and it would still run hot, but it wouldn't be like a 70 amp power stage doing 70 amps output. That tends to be very impractical. But anyway, so that's the 3170 graph. Here we have the MP86957. Now, you'll notice that the 3170 is only rated at 1.8 volts, and the reason for this is that these parts are generally, like, the smart power stage standard was sort of designed for Intel server CPUs, and Intel server CPUs run on 1.8 volts. So, yeah, a lot of smart power stages will be rated at 1.8 volts, which is really annoying when you then try to, like, figure out how effective they are going to be for powering a GPU, because what you'll notice from the MP86957 graph here, which is rated at both, yeah, that's rated at both, I'm on the wrong, rated both at 1.8 volts and 1.2 volts, is that actually at 1.8 volts, it actually produces more heat than it produces at 1.2 volts. But you'll also notice it's more efficient at 1.8 volts than it is at 1.2 volts. But that's typical power stage things, so don't really worry about that. The main point here is that, yeah, like on a 4090 where you're not even going to be running 1.2 volts, the actual heat output is going to be lower for the current that these power stages are outputting. But anyway, so I took these two performance graphs and I sort of slapped them on top of each other, as you can see here. And I've scaled them so that like the 60 amps over here and the 0 over here line up with the 0 and 60 over here. I've also done it so that like 12, 12, 14, 14, right? So these all of the numbers like line up. And what you'll notice is that the FDMF 3170 is like the 1.8 volt output performance of the 3170 is basically right on top of the 1.8 volt output performance for the MP86957. There is a slight difference towards the end of the chart where it looks like the 3170 might actually be more efficient at very high current outputs, but this could also just be down to differences in measurement or test methodology between monolithic power systems and on semiconductor, because as far as I know, there isn't a official standard for how you're supposed to rate your power stages. So yeah. Also, this difference is so small that I would generally consider it irrelevant. So yeah. It could be like there could be like a difference of like what inductors are being used or something that could be affecting that. So functionally, this change, like the switch from the MP8695, like from the 3170 to the MP86957, in terms of like current handling capacity, it's not really making a difference. In terms of functionality, the MP86957 could have some like protection features working better in combination with the MP2891, but the 3170s already had a bunch of the like standard, protection features that you see on a lot of smart power stages. And then, of course, like these are smart power stages, so they have built-in overcurrent protection, over temperature protection, temperature monitoring, current monitoring, all the usual smart power stage stuff. There's just like some extra protections on top of that are manufacturer specific, but we're not going to get into those because they're annoying to explain what they do. So anyway, and I'm also not sure which one of them is actually better, so we're just like going to avoid that. So yeah, that's sort of the most noticeable difference in the power delivery is like we have monolithic power systems, power stages now on the Matrix instead of the on semiconductor parts that were on the Strix. But I don't know if this is a supplier thing or if this is an actual design choice, because either of those seems equally likely to me. Because yeah, from a performance perspective, it actually makes no difference. Anyway, or makes little to no difference. We'll just go with no difference, right? Like I showed, you saw the graphs, as far as I'm concerned. So I'd consider that no difference. So, yeah. In fact, this PCB is so similar to the Strix PCB that I wouldn't be surprised if ASUS actually started using this PCB for their Strix cards. And that wouldn't be like, and you might be like, wait, what? They'll like change the PCB without like changing the name of the card. And yeah, that's actually pretty standard practice. If I'm not mistaken, there's like two different variants of the GTX 980 Ti Strix PCB. There's two different variants of the R9 Fury PCB. And ASUS isn't the only like manufacturer that does this. Like there's several different variants of Gigabyte 4090 PCBs all under the same model number, and those are actually more significant differences than what ASUS is doing here. The Gigabyte 4090s is like different voltage controller, completely different power stages, like very big differences. Though the thing that is consistently preserved is the physical location of all of the tall components. Which means heatsink compatibility doesn't change, right? Because you can, as long as like your inductors and your tall capacitors are in the same places, you can sort of swap, like those are the things that affect the heatsink compatibility. So you can sort of change everything else, and as long as the tall components are where they should be and all of your screw holes are where they should be, yeah, you can just kind of change PCBs without really doing anything to the heatsink design. So I wouldn't, and this PCB, at least at a glance, looks so similar to a Strix that I wouldn't be surprised if ASUS actually started using this PCB on Strix cards. But I am not sure if they're actually doing that, and I have no but I would not be surprised if they did do that. Anyway, I guess other than that, I guess I could point out the fact that there's some modding functionality over here for overclocking, but there's no clear labeling as to what any of this does. And I don't have any like extra information on how this is set up to function. Personally, I would like if I had one of these and I wanted to push it to the limit, I would just use the connector over here to hook up an Elmore EVC2 and just get direct control of the MP2891. Because yeah, this is a fully digital controller, so the Elmore EVC2 can set both the memory voltage and the core voltage on this card. And I think, if I'm not mistaken, this card might actually have support for setting all of the, I think there might be some, like, special internal tool from ASUS for this card. I might be misremembering that, but I think there is a tool for this card to set all of the voltages. NVIDIA's probably not thrilled about the fact that that exists. Anyway, yeah, so those are sort of the, like, standard things that I cover in my PCB breakdowns, but the main reason I actually decided to finally force myself into making this video, because I've been sitting on these photos for a very long time, is what ASUS did with the 12-volt high power connector. So this connector is notorious for being a pile of trash that melts. And the reason it melts is because the pins don't make proper contact. Usually this is blamed on user error, but like I don't know how, like I'm not interested in investigating NVIDIA's power connector. So anyway, but ASUS came up with a what I would consider a valid solution to figuring out if this connector is actually plugged in properly or not, which is just put 6 shunt resistors on it, right? Because the whole issue, so the usual issue with this connector is there is no way to figure out if one of the pins on this connector lost contact. Now, I know a lot of people might be like, oh, but you have these 4 sense pins, and it's and sure, but I'm still not seeing how these 4 sense pins are supposed to tell you if your 12-volt pins are actually making good contact or not. So as far as I know, these 4 sense pins are primarily meant to just set a power limit, which seems kind of pointless, but anyway, yeah, no. So ASUS instead, or the work, is it a workaround? Yeah, I guess it's a workaround. So basically what ASUS did here is they've put 6 shunt resistors on the 12-volt high power connector, which means that they have a connector they have a connection for every single 12-volt pin in this connector, right? So you can see the little polygons, I guess that's the term, for each of the 12-volt pins of the power connector over here. And the idea behind this is extremely simple. If you have 6 shunt resistors and a whole bunch of INA 3221s, which we do, right, that's what these 2 chips are over here. And for some reason, there's a third INA 3221 over here. I have no idea what that is for, because each of these has 3 inputs. I don't know why there's 3 of them, because we do only have 6 shunt resistors that you need to monitor. But anyway, yeah, we've got 3221s, and what these do is they just measure the voltage drop across each of these shunt resistors and use that to calculate how much current is flowing through each pin of the 12-volt high power connector. So now, if you have a scenario say, you might have, under ideal conditions, you would expect the current flow through the connector to be something like, okay, we'll just go with 10 amps, 10 amps, 10 amps, which I don't think that's above the rating of the connector, but for convenience, we're just going to use the number 10. Okay, so let's say you had 10 amp. Actually, wait, isn't there an easier number for doing this? I think 6 would work better. Yeah, so you could have 6 amps across each pin. And let's say this pin just loses connection completely, right? So this one drops to 0. Well, now you'd see 7 amps on all of the other pins. And the card actually has software that can detect, can monitor the shunt resistors through the INA 3221s. So the card can actually detect when the connector is imbalanced in terms of the current flow through the pins. Because yeah, normally a 12-volt high power connector, just all 6 of the 12-volt pins go into one 12-volt power plane, and that's that. There's no way to tell which pin is pushing, how much current is going through which pin on a standard 12-volt high power, on a standard implementation of the 12-volt high power connector. Whereas with this implementation, ASUS does have the capability to actually check the current flowing through each individual pin of the connector. Which, is certainly a way of checking that the connector doesn't have any weird current imbalances going on. I'd argue we could just have a better connector instead of electronics to make sure that the connector actually works. But, the thing is, NVIDIA probably wouldn't allow ASUS to ship this card with 4 8-pins, so I guess this is the next best thing. But, yeah. Anyway, so that's certainly, as far as trying to deal with the 12-volt high power connector melting goes, I think this is the best solution. Because, like, you can, like, with this, you can actually just check how much current is flowing through each pin. If there's any weird imbalance, the card could, well, I'm not sure if how ASUS actually has this implemented, but, like, worst case scenario, you could just have a system where the card just shuts down the moment it detects a really serious current imbalance in the connector. So, yeah. Alternatively, it could also just give the user a warning in software like, hey, your connector is working itself loose again. Imagine if you kept pushing it. I would imagine that it constantly readjusting the position of the 12-volt high power connector would eventually wear it out. But anyway, so yeah, this is the, as far as I'm concerned, the most noteworthy feature of the Matrix, because this is the only card that I'm aware of that has this, and yeah, it's pretty cool. And honestly, like, it would be really cool if ASUS just took this PCB and started using it on Strix cards, because then Strix cards could have this functionality as well. So, yeah. Anyway, below that we have the standard set, standard set of shunt resistors that 4090s require for their power limit enforcement, as well as this shunt over here, right? So this one's for monitoring the power coming in through the PCIe slot, and then these three over here. So these monitor the total power going into the card. This one monitors the power going into the memory. So the power sort of splits off through this one, and then this inductor goes over to the memory power phases. So yeah, and this is like the standard configuration of shunt resistors for a 4090. You have that on every single card. And then there is a chip called a UP something something, and it should be somewhere here. Yes, we have the US 5650, not the UP. Yeah, so you have the US 5650, and this is a 4-channel shunt monitoring chip. So this is like this is very similar to the INA 3221s, but if I'm not mistaken, this thing actually goes, has a faster update rate. Which is just a requirement for NVIDIA's power management boost algorithm stuff to work at the speeds that they want it to work at. So, yeah, but the US 5650 is standard on 4090s, and no, it does not give you the capability to check which of the pins on the 12-volt high power connector is about to melt, because, well, it can only monitor four shunt resistors, so it couldn't monitor 6 of them. And the other thing is, it's connected to these 4 shunts, like the 4 shunts that you usually have, and those shunts are just used for measuring the total power going into the card and the memory. So, yeah. Anyway, that's the 4090 Matrix PCB. It's basically a Strix with like an advanced current monitoring system for the 12-volt high power connector, which is pretty neat. Like the current monitoring system that they put onto the card. I would imagine that this, like, in terms of parts cost, this isn't really that expensive. So technically other manufacturers could copy this as a workaround for how terrible the 12-volt high power connector is, but we could just have better connectors. I don't know if that might be cheaper than, a whole bunch of electronics to verify if the connector is properly plugged in. So, yeah. Anyway, that's everything I wanted to cover in this video. I mean, for me, it was mostly to point out this, because I do think this is actually a really cool feature, and yeah, why don't we see this on more 4090s? Because this seems like the best way to solve the 12-volt high power connector, because it's just like, well, if you actually check how much current is flowing through each of the pins, it makes it really easy to tell if one of the pins is like working way harder than all the other ones or something. So yeah. Anyway, that's it for the video. So thank you, ASUS, for the photos. And thank you for watching. Like, share, subscribe, leave any comments, questions, suggestions down in the comments section below. If you'd like to support what I do here with actually hardcore overclocking, I have a Patreon. There's a link to that down in the description below. There's also the HOC Teespring store where you can where you can pick up shirts, hoodies, posters, you know, the usual YouTuber merch. And I've also got a Bandcamp. There's a link to that down in the description below. And yeah, that's it for the video. So thank you for watching, and goodbye.